So, good morning, everyone. It's 8 o'clock at Eastern Coast. So, let's start our work. And first, let me introduce our today's speaker. This is Ronald Murphy from one of the most famous group working on gamma ray emission. Historically led by Rian Ramazzi. Ronald graduated in 1985 from University of Maryland with Rian Ramazzi as advisor, and he had 1 year of postdoc at Goddard Space Flight Center, then started in naval research laboratory focused on theoretical calculations of high energy emissions from interactions of ion accelerated in solar flares, and mainly worked in and is working in close collaboration with Jerry Sher, University of Maryland, and Ben Kozlowski from Tel Aviv University. So, Ron, please go ahead. You have total 30 minutes, 25 for talk and 5 for discussion. So please go ahead.
Great, thank you. Hello, everyone. Thank you, Gregory, for inviting me. I'll be talking about high energy emissions from solar flares. First, I'll give an overview of the 5 most important emissions that are observed and how they can be used as diagnostics to give information about the flare process. And along the way, we'll have some examples of flare analyses. But first, I should put flares into a broader context of solar eruptive events. Flare is only one part of that. In the lower corona, magnetic reconnection provides energy to accelerate particles. These particles go down the legs of magnetic loops, interact in the denser chromosphere, and produce X-rays, gamma rays, and neutrons, which we'll talk about. But this is done in the lower corona and chromosphere in closed loops. That's the flare. But associated with flares, there are often ejections of plasma and magnetic field called coronal mass ejections, which can move out through the interplanetary medium at often several kilometers per second. Shocks can be produced in front of them. These shocks can accelerate the material in the interplanetary medium, solar wind, also seed particles that are there possibly because of previous CMEs, or maybe even particles accelerated in flares can escape along open field lines and be part of a seed population. These ions accelerated, they move out the interplanetary medium, they get to Earth, and they are the solar energetic particles. But also some of these solar energetic particles accelerated by the shock may be able to make their way back to the sun to interact, or maybe they can connect to magnetic field lines that make their way back to the solar surface in some other region away from the associated flare. So, looking now at flares in particular, again, all of the elements of the solar atmosphere are accelerated due to the energy release. Electrons, protons heating 3 alphas, heavies, and they go down and interact in the chromosphere. Solar flares are typically between a few tens to a few hundred seconds in the duration. Here's a time profile of X-rays from the flare. Also, I plotted the GOES soft X-ray. This is a thermal response of the atmosphere to the energy input. Flares are typically much shorter and occur on the rising edge of the thermal emission. We know this overall loop kind of model is appropriate because we can see them. We can see the loop in thermal soft X-rays. Here's a Yoko image. We see foot point emission. Here's electron bremsstrahlung at the foot points. We also see some emission associated with the energy release at the loop top. Here's a more recent image from RESI. And so we're fairly confident that this fit target loop model successfully explains most of the radiation from solar flares. So what are the products of these interactions? Again, the electrons produce observable bremsstrahlung. The ions produce a number of products: excited nuclei, radioactive nuclei, neutrons, and pions. And except for the neutrons, none of these are directly observable. However, in secondary processes, they do produce observable emission. So what are the observable emissions? Excited nuclei promptly de-excite, producing line radiation at a few MeV. Radioactive nuclei, they decay according to their various half-lives, and they can decay into an excited state of a daughter nucleus. That daughter nucleus then immediately de-excites and produces additional gamma ray line radiation, but these lines are delayed relative to the prompt lines because of the half-lives of the radioactive emitters. Some of these radioactive nuclei decay via positron emission. These positrons can then slow down and annihilate with electrons to produce the 511 keV positron annihilation line. And again, this line is delayed relative to the prompt lines because of the half-lives of the radioactive emitters. Neutrons, some of the neutrons can directly escape into space and be observed.
But I wonder, is there any additional delay because of positrons are produced high energy or relativistics and they have to be thermalized first?
Yeah, most of the positrons, of course, are from radioactive nuclei, and they're just, hundreds of keV. They're not relativistic. The positrons from pion decay, which I'll talk about in a moment, they of course are. But typically, for a typical flare spectra, the half MeV line is dominated by positrons from the radioactive nuclei. And so there may be some small amount of extra delay due to slowing down time, but it's not great.
Okay.
The neutrons, those that escape, those that move upward can escape into space and be observed at Earth and even on the ground in neutron monitors. Those neutrons that go down into the sun can be captured on hydrogen, which produces deuterium, and the binding energy is released as the 2.223 MeV neutron capture line. This line is again delayed relative to the prompt lines because of the time it takes for the neutrons to slow down and thermalize and be captured. Finally, pions, these are prompt. Neutral pions decay directly into two gamma rays. Charged pions decay into positrons and electrons, which produce observable emission via bremsstrahlung. And again, the positrons, as we just said, can slow down and be captured and produce additional positron annihilation line. Fundamental thing we need to make calculations are the cross sections, and this is challenging because ions in solar flares are accelerated over broad energy range, few MeV to more than a GeV. And ideally, you want these cross sections to be measured in laboratories, but of course, the range is insufficient. Not all reactions are measured, and so we cannot rely solely on measurements. We're forced to use theoretical evaluations. Nuclear reaction codes we use typically currently is TALIS, an excellent program, and the final cross-section that we use is an evaluation based on combination of measurements we do have and nuclear reaction theory and empirical rules. We've been working on cross-sections and improving them since the 80s. Okay, looking at nuclear de-excitation lines in particular, here is a level diagram for a light nucleus, nitrogen, and you see there's only a couple of possible nuclear states, and so there's only a couple of lines that can be produced by nitrogen. Heavier nuclei, though, can become very complicated with lots of potential lines. Iron has hundreds, and so in fact there are thousands of de-excitation lines produced in solar flares. These de-excitation lines can be categorized in two broad categories: direct reactions and inverse reactions. Direct reactions are where the projectile is a light nucleus, proton, alpha, or helium-3. Inverse reactions are where the projectile is now the heavy nucleus. Both of these kinds can be further split up into three types of reactions: inelastic, where the nucleus is simply excited and then de-excites to produce the gamma ray. Spallation reactions of a heavier nucleus can produce that same nucleus in an excited state, and fusion reactions of a lighter nucleus can also produce the given nucleus in an excited state. So now looking at the direct and inverse reactions in a little more detail, the gamma rays that are produced are Doppler shifted due to the recoil velocity of the emitting nucleus. In a direct reaction where the projectile is light and the target is heavy, the recoil nucleus velocity is low, and when it de-excites, the gamma ray is only weakly Doppler shifted, in contrast to the inverse reaction where now the projectile is heavy. The recoil nucleus retains much of the velocity of the original nucleus, and so when it de-excites, the gamma ray is strongly Doppler shifted. As a result, direct reactions produce narrow lines, full width half maximum of a couple of %, whereas the inverse reactions produce broad lines, 20%. Excuse me. Calculation of these inverse and direct reaction gamma ray lines for the carbon-12 4.4 MeV line. You see the narrow line and the broad line. And so we see that the relative yields of narrow lines depend upon the target heavy elements. And so the relative yields depend upon the abundances of the ambient medium, an important diagnostic. Of course, they also depend upon the relative abundance of the projectile nuclei. And finally, because the cross-sections for the various lines have different energy dependencies, the relative yields also depend upon the shape, the spectral shape, the shape of the energy spectrum of the projectiles. On the other hand, the broad lines now depend upon the abundances of the accelerated heavy elements. And so this is an important diagnostic for the accelerated particles. It also depends upon the ambient helium-4 hydrogen ratio, and again, of course, on the spectral shape of now the accelerated heavy ions. So this line shape can be explored to give us some...
Ron, can you comment why the broad line shows sort of saturation or like flat top, or it's just cartoon?
It turns out that an isotropic distribution of excited nuclei, monoenergetic excited nuclei, is actually a flat top distribution. It has straight sides and a flat top. You can derive this directly from the Doppler shift formula. And so what we see in flares, of course, is a distribution of energies. We see a distribution of angular of projectile directions. And what you get is a composite of that. And in the broad line, you get to see that flat top is retained more than, it's actually there in the narrow line too. It's just it's so narrow that you can't see it.
Okay. Mm-hmm.
Okay. So now the line shape. What I show here in red is the line shape from a isotropic distribution of protons of the carbon-12 4.4 MeV line. The blue is the shape of the line from alpha particles. Because they're heavier, the recoiled nucleus has a higher velocity, and therefore there's a broader Doppler shift, and the total line is then a combination of these two. And the subtle difference between these two line shapes of protons and alphas can be used with good spectroscopy to derive the accelerated alpha-proton ratio, which Keener did here and got a constraint on the alpha-proton ratio. The line shape depends upon the angular distribution. Here I show in green for the same carbon-12 line the line shape from isotropic, and in red is a downward beam. These are the expected line shapes when the flare is located at disk center, right here in the middle of the sun, so that the beam is moving away from us. And you see the maximum Doppler shift here of the line from that angular distribution. When the flare moves to the limb, over here, the Doppler shift is less. And this can be exploited to determine the angular distribution of the interacting particles. Here are measurements for several flares at varying locations on the solar surface. And this is a calculation of the expected Doppler shift from downward isotropic accelerated ions. And you can see that the measurements are consistent more or less with the downward isotropic. What's important is that the interacting ions are definitely not isotropic, as all the lines would be up here. All the line centroids would be here. We have a code that includes over 190 explicit lines, and this is a calculation. You can see the narrow lines here. I've also separated the broad lines here so you can see them. And the thousands of other lines, which we don't explicitly include in the code, are also included as a continuum, which fills in here. And one last thing with the excitation lines, again, because the cross-sections for the various lines have different energy dependencies. Here, the solid is the cross-section for the neon 1.6 MeV line. The dotted is the cross-section for the oxygen 6.1 MeV line. Because of this difference in energy dependence, the ratio of these two lines is quite sensitive to the steepness of the accelerated particle energy spectrum. Here we've assumed a power law. This is the power law index. So a measured 6.1 to 1.6 MeV line ratio can then be used to derive the index of the accelerated particles. And Reuven did this a long time ago for a number of flares, so that most flares have indexes between 3.5, 5.5, average around 4.5. One final thing, the cross-sections are fairly low energy, and so this is the depth distribution of the interactions in the solar atmosphere.
Ron, there is a question from someone,
Yes.
from Alexandra, I think. So go ahead, Alexandra.
Thank you. Excuse me. I had a question on previous slide. Could you please return to me?
I'm sorry, I can't quite hear you.
Can you come back to previous slide and she asked question? This one?
Yes. Yes. Thank you. Well, you say that we can derive proton power index based on the ratio between these two lines.
Yes.
About 6 MeV and 1.6 MeV. Yes.
Yes.
Well, and I've done this estimation of proton power index based on the ratio of neutron capture line and nuclear lines between 4 and 7 MeV. So, are these results coincide or not, or you will
Yes.
discuss it later?
Good question. Eventually we'll get to that. We'll discuss the neutron capture, we'll discuss all of the radiations, and we'll bring it all together in the end, and we'll show how the various ratios can be used to derive the index across various energy ranges. So all this will become clear eventually, okay?
Oh, thank you. Excuse me. Thank you.
Yeah, no, here we go. I think we'll skip this. We're getting a little behind here. Okay, moving on to positron production and annihilation. Again, two sources, radioactive positron emitters and pions. The positron emitters have various half-lives. They produce a daughter nucleus and emit a positron. And pions, again, they decay into positrons also. And we have a code that calculates the positron production from a large number of such emitters. Positrons annihilate. It's a very complicated process. We're not going to go through it in any detail, but a few words are important. Overall, there's two general ways positrons can annihilate, either directly with electrons, in which case you get 2 half MeV photons, or it can produce positronium first. Decay, annihilation from positronium produces both a line and a continuum. Positronium can be produced in two possible spin configurations, either with the positron-electron spins antiparallel or parallel. Antiparallel, there's only one possible Z Z component, and so this is called a singlet state. But when they're parallel, there are three possible Z components, and this is called the triplet state. Positronium is always formed in a 3-to-1 ratio of triplet to singlet. Annihilation from the singlet state produces, again, 2 half MeV photons. But annihilation from the triplet state produces free photons of energies less than half MeV distributed in a continuum below the 511 line. And in high density, high temperature medium, collisions can spin flip the triplet state to the singlet state, upsetting the original 3-to-1 ratio. Annihilation is very complicated with all of these possible paths to final annihilation. And each of these paths produces a annihilation line of a specific shape. And the final total shape is a combination of all these possibilities. And the paths through here depends on the temperature, the density, and the ionization fraction of the medium, with the result that for various assumed medium conditions, you can get a variety of annihilation line shapes. And this can be exploited to learn about the conditions at the annihilation region, for example. But this will take high resolution spectroscopy, like the germanium detector on RESI. Here's an example of a measured positron annihilation line. You see it's only a few keV wide. Here is a time history of the measured width in the October 28th flare, and you see that the line did an amazing thing. It was coming along at a fairly broad value, and then over a 2-minute period, it suddenly became very narrow, as if it got much colder, for example. And the explanation of this is still a mystery. So we can use the annihilation line yield, again, to derive information about the shape of the accelerated ion spectrum. But this is only relevant where the cross-sections are important. So if we take a ratio of the annihilation line to, for example, de-excitation lines, here's the cross-section for de-excitation lines, here's the cross-section for a typical spallation reaction to produce a positron emitter, we see that the ratio is going to be relevant in this energy range, between a few MeV to maybe 50 MeV. And so here's the ratio of the positron annihilation line to the carbon line as a function of accelerator particle power law index. And you see that it's very sensitive and useful. I don't need to talk about that. Neutrons. Neutrons are produced by a number of reactions, PP, P alpha, alpha alpha. These are the most important. Projectiles on the heavier elements also produce neutrons. Here are cross sections, and you can see the cross sections for the heavy elements are quite strong, but of course heavy element abundances are down by 4 orders of magnitude. So in fact, the most important neutron producing reactions are the PP, or the P alpha and the alpha P reactions represented by the cross section here. Neutrons that are moving upward can escape. They're not charged, so they move in straight lines. They can make it to the Earth and be observed. Of course, free of the nucleus, neutrons decay, and when they decay into a proton, the proton can be trapped on a magnetic field line. Decayed protons can be also observed, have been also observed. Neutrons that go down into the solar atmosphere, as we said, are captured on hydrogen, produce deuterium, and the neutron capture line. We have a code that calculates the neutron energy spectrum from solar flares. And this energy spectrum shape is quite sensitive to the spectral shape of the accelerated ions. And so comparing calculated neutron spectra with measured neutron spectra is another tool for determining the shape of the ion spectrum. But of course, it must be remembered that the neutrons do decay on their way to the Earth. This is the spectrum at the sun, that released at the sun, but by the time it gets to 1 AU, All the lower energy ones have decayed away because of their longer transport times. Neutron capture line, as I said, deuterium is produced because the cross-section for capture is proportional to inverse velocity. The neutrons first thermalize before they are captured, and they thermalize in the dense photosphere where capture is probable. And so they're very deep in the photosphere. And as a result, even though the neutron capture line is the strongest solar flare line, it can be significantly attenuated, especially when the flare is near the limb of the sun. And again, these neutron capture lines are delayed by about 100 seconds due to the time it takes to thermalize. And because it's thermalized, the line width is very narrow and is of no diagnostic value. So using the ratio of the neutron capture line to a de-excitation line, again, we can use this to determine the spectrum of accelerated particles, but now there is a dependence on heliocentric angle. And so using such calculations, you can determine the spectral index, and then the fluence in any given line then will normalize and give us the total number of accelerated ions. For example, the June 4th flare, the spectral index was determined to be 4.2, and the number of the number of accelerated protons was 7 times 10 to the 32. Finally, pions. Here are the cross sections for P alpha production and PP production. Very high energy, thresholds of 100, 200 MeV, 300 MeV, very high energy reactions. The neutral pions produce 2 gamma rays, 67 MeV each, but then they're highly Doppler broadened. The charged pions produce positrons and electrons, which produce continuum emission via Bremsstrahlung, and some of the positrons can slow down and produce more 511 line radiation. We have a code that calculates the pion spectrum. Here's the total pion spectrum with the various components, neutrals, Bremsstrahlung, and annihilation. And the shape of the pion spectrum, again, is very sensitive to the accelerated ion spectral index. And directly fitting measured pion decay spectrum, as, for example, observed with Fermi-Lat, can again provide a measure of the accelerated ion spectrum, but now it's only above 300 MeV, the threshold for pion production. So finally, putting it all together, we can use our codes to calculate the complete gamma ray spectrum from a solar flare. And this is what I show here. In green are the de-excitation lines. See the neutron capture line, the positron annihilation line, pion decay. I've also included the electron Bremsstrahlung, which I haven't talked about. This was just about the ions. And I've even included here the thermal emission from the flare itself. So here's the entire spectrum, calculated spectrum from a solar flare. And over here are a couple of examples of measurements. This is a measurement of the gamma ray spectrum from the June 4 flare using the sodium iodide moderate resolution OSSI detectors. You can see the gamma ray de-excitation lines, see the neutron capture line broadened here because of the instrument response, and also similarly the annihilation line is broadened. Here is the spectrum with the high resolution RESI instrument, and now you get to see the neutron capture line and the annihilation line are narrow as they should be. So to get back to the original question, we can use these ratios to again to derive information about the accelerated particle spectrum. But it's important to remember what energy ranges these measurements are relevant to. Here's a couple of de-excitation line cross sections. Here's a typical radioactive positron emitter cross-section. Here's a neutron production cross-section, and of course pions. You see they vary over a wide range. The excitation lines are produced by ions of a few tens of MeV. The annihilation line extends this up a few tens of MeV more. Neutron capture line even further, and pion decay is above the threshold of 300 MeV. So when we calculate the various ratios, for example, here's pion decay to the neutron capture, here's two de-excitation lines. All of these can be used to derive spectral indexes, but only across the energy ranges that are relevant for the two yields that you're using. And so that's my final slide. Here is a recent measurement of the solar flare by the Fermi, GBM, and LAT instruments. And you can see the gamma ray lines, the pion decay emission, neutron capture, positron annihilation. So we can use line ratios again to get information about the accelerated particles. In particular, if we use the neutron capture to de-excitation lines, then we get an index of 3.2. But this ratio is only relevant from a few MeV to maybe 30 or so MeV. So the 3.2 covers this energy range. If we use the pion decay to neutron capture, we get a value of 4.3, but that's only relevant from a few tens of MeV to 300 MeV, this energy range. And finally, we can directly fit the Fermi LAT data from the pion decay, and we get an upper limit steeper than 4.5. That's relevant to above 300. So we see using all of these various ratios, we can derive the spectrum, in fact, over a broad energy range. And your original question was, are they consistent? And the answer is not necessarily. In fact, as expected, the spectrum seems to steepen with energy, as might be reasonable from typical acceleration mechanisms. And that's my last slide. So, any questions?
Okay, thank you very much, Ron. It's very interesting and very instructive, I would say, in a nutshell. So please, we are open to discussion and questions. So please unmute your microphone when you ask questions. Alexandra?
Thank you very much for the talk. And I have one more question, maybe not one. Could you please estimate positron energies for positrons produced through beta decay and positrons produced through pion decay? What are they approximately?
I'm sorry, I didn't quite catch all that. You're asking me to estimate what precisely?
What are positron energies from?
Positron energies, yes. I'm sorry, I have a...
Yes, of course. No, typically from radioactive emitters, the positrons emerge with a few MeV, a few hundred keV, something like that. But of course, from pions, it's hundreds, 100 MeV even. So it varies widely. Is that the answer that you were looking for?
Yes.
Okay, Alexander, more questions? Just be quick, please. Yeah. Well, Alexander, do you have more questions at the moment?
Yes, I have.
Go ahead.
Yeah, thank you. Maybe.
And speak louder, please.
Much louder, please.
Yeah.
Yes, I'll try. Well, maybe you told about that, but I missed. And what are decay times of annihilation line for positrons produced through pion decay and beta decay? Well, what are the times of delay emission of annihilation?
Right. Okay. Again, the positron emitters, they of course have a wide range of half-lives, from fractions of a second to tens, hundreds of seconds. So the positrons from those are produced over those kinds of time scales. The pions, of course, they decay immediately, so the positrons are produced immediately. But then, of course, they have to annihilate. And again, for typical flare spectra, index of about 4, most of the positrons come from radioactive emitters. And so they are delayed according to those various half-lives, a couple hundred seconds typically. And so now they must slow down. And but they're only an MeV or so. And so that slowing down time appears to be maybe on the order of 10 to 20 seconds at most. On the other hand, the pion produced positrons, they will take perhaps 100 seconds to slow down. But again, in typical flares, they don't make much of a contribution to the half MeV line.
Thank you.
Thanks.
Ron, I have one question. So you demonstrated that a lot of physics and a lot of diagnostics can be learned from details of line ratios, line to continuum, etc. But on the other hand, the standard products like in OSPEX, like templates, they already assume some mean values, mean distribution, mean spectral index. So what is the basically right way of learning this?
Right. In principle, what you should do is to exploit all the parameters on which these emissions depend, and that would be the shape of the spectrum, and that would be the abundances. And so those parameters really should all be varied when you fit solar flare spectra. But of course, that's a lot of parameters, and it would put big demands on the quality of the data. And typically, unfortunately, flare gamma ray data are not of sufficient quality to do it that way, and so compromises must be made. Typically, what Jerry's done is he's assumed an abundance, for example, coronal, and he'll then calculate a spectrum for that abundance and fit with that and vary the spectral index. And so he does a lot of fits for various spectral indexes, all assuming coronal, and gets chi-square minimum, and there's a determination of the index. And then he might then assume a different abundance, photospheric, do the same thing, and see how the spectral index varies. So again, in general, there are a lot of parameters that should be varied simultaneously to optimize, but in practice that can't be done. So you've got to make some assumptions about them, do the fits that for the parameters that you are interested in, and then be sure that you've included additional systematic uncertainties to account for the fact that you're not optimizing all parameters simultaneously.
Yeah. Okay, thank you. More questions? I have very final, I believe, quick question. Can you comment at all on possible role on helium-3 enhancements or abundances? Does it play any special role or provide some additional diagnostics?
Right. I didn't talk about helium-3 here in particular, and in fact, Vince and I just recently completed a study of accelerated helium-3 producing de-excitation lines, and the helium-3 has been ignored in the past because no one thought that it was relevant, but now we know that there are solar energetic particle events, the so-called impulsive class, where helium-3 is enhanced by many orders of magnitude over what is expected in the solar corona. And so if those same enhancements are in the accelerated particles in solar flares, we found that indeed it can affect the gamma ray spectrum, and there are specific lines that helium-3 is particularly sensitive to, and they can be used to derive the helium-3 abundance in solar flares. directly from a spectral analysis. And we did that for some SMM data and found that indeed helium-3 was enhanced by about 2 to 3 orders of magnitude over the expected coronal values, similar to the impulsive SEP events. And generally, it doesn't affect the spectrum too strongly. The cross-sections for helium-3 reactions are pretty much similar to the cross-sections for protons and alpha particles to produce the same line. But again, there are a few lines that are particularly sensitive to helium-3, and those are the ones that we exploited to derive the helium-3 abundance. But I don't think that the addition of helium-3 would affect things like the overall abundance of the ambient medium, for example. If you were trying to determine the ambient chromosphere abundance using gamma-ray spectroscopy, I don't think helium-3 is going to play a big role in that. But does that answer your question?
Yeah, sure, absolutely.
Mm-hmm.
So I see that all microphones are on mute, so it means that we do not have any further questions, and we are slightly behind our schedule. So
Right.
Let me thank our speaker again for really very interesting and instructive talk.
You're
Thank you
welcome.
very much, Ron. So I stop recording here and we change to another part of our meeting. So
All
thank
right.
you very much.
Thank you, Gregory. Bye-bye.
Bye.